Hello and welcome to Chapter 1, our Introduction to Groups. We're going to do this in two parts. First one being Symmetries of a Square, and the second video is going to be on the dihedral group. So as stated, let's start with Symmetries of a Square. Now, why are we doing this? What's our motivation? Well, think about if you start with like a piece of paper on your desk, and you pick it up and you move it around. You flip it, you spin it, all sorts of different things. You put it back down. And what do you have to do to it so that when you put it back down, it's back in the original space it occupied? Not necessarily in the exact same space, but if the paper was originally horizontal on your desk, when you put it back down, it has to be horizontal again. So what types of moves allow a shape to occupy its original space, and what types of shapes fall into this category of being able to move them around and bring them back to the original space? So if you've ever played with those children's games where you've got the star fits in the star shape and the orange, or sorry, the round shape fits in the round hole and all those types of things. It's kind of like if you take the rectangular piece out of that puzzle, you can spin it and rotate it and flip it and stick it back in that little hole, but only if it fits, right? So there's only certain moves that you can do in certain combinations to get it back into that same occupied space. Now it's going to be a lot easier if you guys have your own piece of paper or cardboard or whatever in a rectangular shape and label it and kind of follow along with these things so you can visualize what's happening. So let's start with a rectangle. Now I know this is symmetries of a square, but remember a rectangle is, similar to a square, right? A square is a very specific type of rectangle. So we're going to deal with rectangles for right now just to see when things work and when things don't work, because a square kind of becomes a boring example. All right, so let's say we start with our rectangle oriented like this, oriented horizontally, meaning that the long edge is horizontal. And then we're going to rotate it counterclockwise. Really doesn't matter if you do clockwise or counterclockwise, by the way. And what do we get? Well, we get that. It's now oriented vertically, which is not occupying the original space, right? It doesn't fit back in the hole. If the dotted line represents that rectangular hole that's in the puzzle piece no longer fits. But what if we rotate it 180 degrees? Well, then it's going to fit in that hole again. Is it back in its original place? Hopefully you're all saying no, because it's not. It's been rotated 180 degrees. It just has symmetry that when you do 180 degrees, it looks the same, right? So that's kind of what symmetries are all about, is what can we do to something so that it appears to look the same? It's in the same general shape and location, but not necessarily in the exact original place. So a 180-degree rotation returns it to its original space, but not its original position, whereas a 360-degree rotation returns it to its original space, i.e. it fits that hole again, but it's also in its original position, right? Because we all know if we rotate anything 360 degrees, it just goes right back to where it started, right? Any shape whatsoever. So 90 and 270, those won't work for getting it back to its original space. But 180, 360, and basically any multiple of 180 will. Okay, to visualize these better, you're going to want to start labeling things. So if you label the four corners of the rectangle, then you can see that if you rotate it 180 degrees, which we're going to call R sub 180, it's in the same space, right? It's still a horizontally oriented shape, but A is no longer in the upper left corner. It's in the lower right, right? And B is no longer in the upper right. It's in the lower left, and so on and so forth. It's been rotated. So that's where it's, we'll say it's symmetrical, but it's not exactly the same. Right? These are kind of where symmetries come to. All right, what about flips? Again, here's our original orientation. This is what we call R sub 0, right? So when it's in this place with the four corners in that order, that we're just going to think of as R0, kind of its origin space. Technically, r sub 0 means a rotation of 0 degrees, but if we rotate something 0 degrees, it hasn't moved, right? It's kind of in its original space. So just kind of think of that as that's the original orientation of this thing, and then we're going to move it around, flip it and whatever, and then kind of see what happens. So let's flip it horizontally and vertically. A single flip about the horizontal axis. So remember, a horizontal flip means you're flipping up and down. You can see that the A and B's are now down here and the C and D's are up there. And that's not back to its original position, right? It's symmetrical, but not in its original position. But if we flip it again, it would be back to where it was, right? If we flipped it horizontally again. Now, this is what happens if we do a vertical flip. So instead of flipping up and down, the vertical flip means we flipped this way, right? We rotated basically around the vertical axis. And now the A has gone from the left to the right, the B has gone from the right to the left, and so on and so forth. It's symmetrical, but not in its original position. If you did a second flip, it would go back. And this makes sense, right? You know, think about any thing that only has two sides, right? A sheet of paper, a mirror is right. So if you've ever seen a mirror, you know, a mirror reflects on one side and it has like a gray surface on the other. So it's a great visual so if you're looking at a mirror where you can actually see yourself, you flip it in any direction, either horizontally or vertically, and all of a sudden you're just looking at this gray surface. But then if you do that same flip again, boom, the mirror's back to facing you, right? So anything that just has two sides like this, if you do two flips, you'll always get back to where you started. You kind of go around the horn, just like 360 degrees goes all the way around the horn. Okay, so here's what we have so far. 0 and 180 degree rotations we call R sub 0 and R sub 180, or you can just call them R0 and R180. Flips about the horizontal axis we're going to call H for horizontal, and flips about vertical we're going to call V. With that in mind, we now have a shorthand that we can start investigating things. Like, what if we rotate and flip? And in which order, right? So rotate, flip, or flip and rotate, do different things happen? What if we do a horizontal flip and then a vertical flip? And what about if we do a vertical and a horizontal, right? It's always nice that if you do one thing and then another, ask yourself, what if you do those two things, but in the other order? Is it going to give you something different? Because when it doesn't, that becomes a very special thing that we'll talk about later. So it's always good to ask what happens when we do the same two things, but in the opposite order. Okay, so remembering our only rotation that changes the rectangle's position is a 180 degree rotation. So that puts it, you know, back in the same position, but the letters have been rearranged, right? So it's not in its original position, but it's symmetrical. And then we have one horizontal and one vertical, because again, we only have a two-sided object. Okay, with that in mind, these are the only things we can really do to it. R0 means we don't do anything to it. R180 is that rotation, the horizontal and the vertical flip. And then a 4x4 table is going to give us all possible combinations of two things, right? Doing one and then the other. So you can see we filled in some of them for us already. And what do these mean? This one right here, that space means first we did no rotation at all, then we did a 180 rotation, and the result to the shape was a 180 rotation. You go, well, no, duh, because if we don't do anything at all and then we do this, that's what we're left with. So you can see that's why this first row is all just a repeat of the header row. Because if you don't do anything and then you do a second thing, you're really just doing the second thing. Same thing with this first column, because it's first we do this one, then we do the second one. And if the second one is nothing, then we're not adding anything to it. So those were easy and kind of trivial. Okay, but look, we've got kind of an identity row around the diagonal, because if first we rotate 180 degrees and then we rotate 180 degrees again, didn't we just rotate 360? And so we're back to the original, the R0. And same thing here. If we do a horizontal flip and then a horizontal flip again, we're back to where we started. Vertical flip and a vertical flip again, back to where we started. Okay, what happens if we first perform a horizontal flip and then rotate 180 degrees? That's asking for this spot here. That's a horizontal flip first and then a 180 degree. That is not the same thing as a 180 degree and then a horizontal flip, which would be here, Those are two different things. They might have the same exact answer, but they're two different things, right? Because we need to keep in mind the order in which we're doing these operations. All right, so let's do this one first, the horizontal, then the rotate. So here's our horizontal flip. So we've already flipped it horizontally, which remember is up, down. So that's why A, B are down here, C, D are up there. And then we're going to do a 180-degree rotation. So from here, we rotate 180 degrees, right? Everything goes basically two spots. So A goes around to here, and we get back to this spot. And what is this from the original square? Or sorry, the original rectangle. Remember, the original rectangle started with A up here, and then B, C, and D. We go kind of around clockwise from this corner. It goes A, B, C, D. That's how it originally looks. And so now when we're looking at this one, do you see how everything's traded places? A and B have traded places, C and D have traded places. We basically have just done a flip in that direction, and that's what we call a vertical flip, right? Because a horizontal flip is over the horizontal axis, and a vertical flip is over the vertical axis, right? So sometimes that's a little counterintuitive, people. It seems like that it's the other way around, but just so we're all talking the same language, the horizontal versus vertical is all about the axis you're rotating on. If you're rotating on the vertical axis, then that's a vertical flip. If you're rotating on the horizontal axis, it's a horizontal flip. So in any case, this gives us a V for vertical. Okay, what happens if we first do 180-degree rotation and then do the horizontal flip? So we're now going to look for the other one, the one up here. So here's our 180-degree rotation. Again, remind ourselves that we started with A, B, C, D. We do a 180-degree rotation, the A comes down here, right? And then it goes A, B, C, D. There it is. Then we do a horizontal flip, which means we're flipping along this axis here, right? Or more precisely, flipping along this axis to get this picture, but you get the idea. So now we have that result, and you can see that it's the exact same thing we had before, which is a vertical flip again. Hey, look at that. We got two V's. So we're already starting to see some symmetry of our symmetry table, that things on opposite sides of the diagonal tend to be the same thing. Do you think that pattern is going to hold? Well, on your own, complete the rest of the Cayley table and see what you get. Go ahead and pause the video and do the rest of them, right? So you're going to be doing a vertical flip and then a 180. Then you're going to be doing a 180 and then a vertical flip, right? You're going to be doing a vertical, then a horizontal flip, and then you're going to be doing a horizontal, then a vertical flip, and seeing what happens with all those. Okay, well, hopefully your table looks like mine. Otherwise, you made a boo-boo somewhere. And what do we notice? They're all the same. As far as a V then an H is the same thing as an H and a V. You know, a 180 then an H is the same thing as a H and then a 180, and so on and so forth. That it doesn't matter in what order we do these two operations. The same two operations in both directions gives you the same thing. Does that remind you of any mathematical things that we have? How about addition? Is A plus B always the same thing as B plus A? Yes. And do you remember what we call that property? What about A times B and B times A, right? Those are always the same. But A divided by B and B divided by A is not, right? So remember we talked about how some things we can do A, B, B, A, and some things we can't. And what was the name we gave that? Well, it's going to be the same thing with these groups. And I'll reveal the secret later if you're not already screaming at the video screen what you know the answer to be. Okay, so what about a square? Well, a square is a special kind of rectangle, right? We all know what a square looks like, but some of you might not have realized that it's just a special kind of rectangle. It's a subgroup of a rectangle. It's basically a rectangle where all four sides are the same, i.e. congruent. So now we have 90 and 270 degree rotations will work with this one, whereas they wouldn't work with a rectangle. And we can now flip about both diagonals D and D prime. just meaning the two diagonals. I should probably change this because it really will work now, right? Okay, so the elements of the set of symmetries of a square, we can now add in the R90 and the R270, and we can also add in the two diagonals to the original set that we had from a rectangle, and we can see that we get more stuff, right? Instead, we only had 4 elements. Now we have 8. So if we were going to make a Cayley table for a square, it would be an 8 by 8 instead of a 4 by 4. A lot more things to look at, but you'll start to see patterns, and you could do it. It's pretty easy. And again, just take a piece of paper. This time, cut it or fold it or something, make it look more like a square. Label the 4 corners, A, B, C, D, and then play around with it and see what you get each time. So on your own, do that. Make the Cayley square for a square, or sorry, a Cayley table for a square, and compare it to the table that you got for a rectangle and see what kind of similarities, differences, and patterns you might see. So again, pause the video and try it, guys. Don't just sit here and wait for me to give you the answer. Actually play around with a piece of paper or cardboard or whatever you got, and kind of discover what's happening, because when you discover it, you own it. If you hear someone tell it to you, it goes in one ear and out the other. All right, so pause it and see what you get. Okay, is this what you got? Well, with the square, we have 8 elements. Those 8 elements being the R0, the R90, the 180, the 270, right? The H and the V for horizontal and vertical, and the D and the D prime for the 2 different diagonal flips. It's non-commutative. That was that word we were talking about, i.e. in the last example, right? Remember here that if we did H and then 180, we got a vertical flip. But if we did 180 and then H, we still got a vertical flip. So A times B equaling B times A, or A plus B equaling B plus A, those are commutative properties, right? Well, when we're dealing with a square, they were non-commutative. It didn't work. A flip and then a rotation wasn't the same thing as a rotation and then a flip, because of those extra rotations, right? Okay, we have 4 rotations instead of 2. We had 2 types of diagonal flips. You had horizontal and vertical flips. Those were all kind of what was happening with the square. With the rectangle, you only had 4 elements. They were commutative. You had symmetry about the diagonal of the Cayley table. And if you notice in the square one, you didn't have symmetry along the diagonal. You only had 2 rotations and no diagonal flips. So basically those were all the differences and patterns that you could have hopefully seen from doing those 2 tables. And that's it for this video.